Welcome class, myself Professor D.S. Rai, Professor Department of Civil Engineering BBD ITM, Lucknow. Today we will take up a subject KCE 602 Transportation Engineering, in which we will discuss design of rigid pavements. The references that we have taken: Highway Engineering by Khanna and Jesto, Principle of Transportation Engineering by Partho Chakravarti and Imesh Das, Pavement Design by R. Srinivas Kumar, Building Material by Dr. S.K. Duggal. The content in the chapter is introduction, Westergaard radius of relative stiffness, critical load position, equivalent radius of resisting section, temperature stresses, stress due to frictional forces, pavement joints. So, as we know, in flexible pavement load is transferred in layer system and grain to grain. Here in the rigid pavement, the load transfer by slab action and load carrying capacity is due to rigidity and high modulus of elasticity of slab itself, and this is called slab action, by which load is transferred to the ground. So, HM Westergaard is considered providing a rational solution for the problem of rigid pavement. And Westergaard theory, in which he said the rigid pavement slab as a thin elastic plate resting on a soil subgrade, which is assumed as a dense liquid. So, upward reaction is proportional to the deflection, P is proportional to delta. So, P will be equal to K into delta, where K is the constant and defined as modulus of subgrade reaction. Unit of K is kg per centimeter square per centimeter deflection, that is kg per centimeter cube. If the P is the pressure sustained in kg per centimeter square by rigid plate of diameter 75 centimeter at a deflection delta is equal to 0.125. The modulus of subgrade reaction K will be equal to P divided by delta. So, P divided by 0.125 kg per centimeter cube. So, this is the one concept that has come. Relative stiffness of slab to subgrade. A certain degree of resistance to slab deflection is offered by the subgrade, dependent on the stiffness or the pressure deformation property of the subgrade. The tendency of slab to deflect is dependent upon its property of flexural strength. The resultant deflection of the slab, which is also deformation of subgrade, is direct measure of magnitude of subgrade pressure. The pressure deformation characteristic of the rigid pavement is a function of relative stiffness of the slab. So, Westergaard defines the terms, the radius of relative stiffness L is equal to ESQ divided by 12 K 1 minus mu square to the power 1 by 4, where L is the radius of relative stiffness in centimeter, E is the modulus of elasticity of cement concrete in kg per centimeter square, H is the slab thickness in the centimeter, mu is the Poisson's ratio and that is taken 0.15, K is the subgrade reaction or modulus of subgrade reaction, that is kg per centimeter cube. A stress acting on the rigid pavement, that is will load stress, and second is the temperature stress. So, critical load position. The pavement, it is assumed that the pavement is a finite length and the width. This is the first assumption. Maximum stress induced dependent on the location of load on the pavement surface. Three types are of the location. First is the interior, anywhere on the pavement remote from all edges. Second is edge, anywhere on the edge remote from the corner, and the corner at a bisector of two edge. So, these are the three locations. Now, equivalent radius of resisting section, the maximum bending moment occurs at the loaded area and act radially in all directions in case of interior loading. If load is concentrated in a small area, what section of the pavement is effective in the resisting the bending moment? So, as per Westergaard, the equivalent radius of resisting section is approximately B is equal to under root 1.6 A square plus H square, where B is the equivalent radius of resisting section in centimeter, where A is less than 1.724 H. A is the radius of wheel distribution in centimeter, H is the slab thickness in centimeter. When A is greater than 1.724 H, then B will be equal to H. So, this is the condition. So, Westergaard's stress equation of the wheel load, interior loading SI will be equal to 0.316 P divided by H square into 4 log base 10 L by B plus 1.069. So, this is for the interior stress. Now, the interior this is edge, not interior. So, this is the edge stress, that is 0.572 P by H square 4 log base 10 L by B plus 0.359, and the corner loading SI will be 3 P by H square 1 minus A under root 2 by L to the power 0.6. So, by this method we can calculate the stresses at the location of the loading. So, here we have discussed already H is equal to slab thickness, P is the wheel load, A is the radius of wheel load distribution, L is equal to radius of relative stiffness, B is the equivalent radius of resisting section. Now, come to the temperature stresses. Due to variation in slab temperature, there are two types of variation. One is the daily variation and second is the seasonal variation. In daily variation, the temperature crosses the slab depth of the slab, where in the seasonal variation overall increase or decrease in the slab. During daytime, the slab gets heated under the sunlight and maximum at midday. So, this is a daytime. Here the bottom of the slab will experience cool and top will experience heat, means more temperature. So, during daytime bottom of the slab remains cooler. To warp at center in upward direction, warping is resisted by self weight of the slab. Top slab will experience compression and the bottom slab will experience tension. In night, bottom slab gets heated and top slab get cooler. Therefore, the end of the slab gets warped in upward direction and self weight of the slab acts downward. Top slab will experience tension and bottom slab will experience compression, this causing warping stress. In this condition, warping stress is resisted by the frictional forces. In daily variation in the temperature warping stress, the difference in temperature between top and bottom slab depends mainly on the slab thickness and the climatic condition. So, average thickness of the slab will be T 1 plus T 2 divided by 2, that is T. So, interior stress will be E, capital E E T divided by 2 C x plus mu C y divided by 1 by mu square, where S T I is the warping stress at the interior in kgs per centimeter square. So, and E is the modulus of elasticity of the concrete, E is the thermal coefficient of the concrete per degree centigrade, T is the temperature difference, C x coefficient based on L x by L in desired direction, and Cy coefficient based on Ly by L in right angle to the above direction. Mu is equal to Poisson's ratio that will that we have taken 0.15. So, STE will be Cx capital E Et divided by 2 and we equal to Cy E capital E Et divided by 2 whichever is higher. We will take whichever is higher. Now, ST corner Et divided by 3 1 minus mu under root A by L. A is the radius of contact. So, stress, this is a stress due to friction forces. So, a stress due to friction forces, the contraction and expansion of the slab take place due to uniform temperature change in the slab. Slab movement are restrained by the intersurface frictional forces between slab and supporting layer. Experience tensile stress at the bottom of the slab and this will causes cracks at the center of the longer span. So, the maximum friction forces developed at the center of the slab and that will be equal to force developed by slab due to the movement with the frictional resistance offered by the supporting layer. So, sigma F into B into H will be equal to L by 2 B into H into W into F. So, sigma F is the tensile stress in concrete slab due to the friction will be L by 2 into W into F. So, we have already W is equal to unit of the concrete, B is the unit width of the slab, H is the thickness of the slab, L is the layer length of the slab, F is the average coefficient of friction. Stress due to friction depend upon the slab length, unit weight of the concrete and coefficient of friction. So, now the come to the critical combination, because there are load stress, warping stress and frictional stress. So, we have to go or choose the critical combination of the stresses. So, during summer the load stress plus warping stress minus frictional stress at the edge region will be taken as a critical combination. During winter the load stress plus warping stress plus frictional stress at the edge region. At the corner region, critical combination occurs at the top fiber of the slab. Slab swarp upward in midnight. The critical combination of stress will be load stress plus warping stress at the corner region. This is the diagram, the tensile stress at the bottom, load and here this is the load at the corner when T is greater than T2. So, this will show the tensile stress at the bottom and compressive stress at the top, whereas the tensile stress at the top and the compressive stress at the bottom. Now come to the pavement joints. Pavement joints. Pavement joints provided in concrete pavement at optional regular interval to allow shrinkage, construction, expansion, curve in the up and down direction. The slab shrinkage due to sudden loss of the moisture also exists. Joint should be placed optimally to maintain a structural efficiency, to relieve warping stress, prevent occurrence of crack. So, see here the type of joints. The first joint is a transverse joint, and in transverse joint there is a construction joint and contraction joint and the expansion joint. In longitudinal joints, the center line joint between two lanes lane joints for multi-lanes, edge joints between the shoulder and the slab, and third is construction joint may be provided in longitudinal and transverse direction. So, see here, this is the tie bars which combines slab of both sides. This is the center line. This is the transverse joint. This is the expansion joint that we have provided here. A dowel bar is placed here. This is the contraction joint, is it? And this is the longitudinal joint. These are the longitudinal joints. And see here, this is filled by the sealant, a elastometric materials. This is filled by the filler of compressibility. This is the dowel bar. Sealant is used as a filler material. Then metal cap half filled with the cotton expansion joint only. So, this is the section elevation across the transverse joint. Is it? So, longitudinal joints providing along a traffic movement, responsible for relieving warping stress by hinge action and preventing irregular longitudinal cracks required when width of slab exceeds 4.5 meter. The type of longitudinal joints are center line joints between two lanes, lane joints for the multi lanes, edge joints between the shoulder and the slab, now come to the transverse joint provided along the perpendicular to the longitudinal joint. This is the longitudinal joints, this is the direction of the moment of the traffic. So, this is the longitudinal joints and this will be the transverse joint like this way. So, this is the transverse joint and this is the longitudinal joints. This will included contraction joints and the construction joint. Construction joints may provided in longitudinal and the transverse in both directions, provided when day works start or stops, and this is very important, full depth joint. Full depth joint, all joints are cut 1/3 to 1/4 depth of the slab to take care of the expansion contraction due to temperature and other conditions, but the construction joint is provided in full depth of the slab. So, it is very important. Now, come to the dowel bars. So, dowel bars to provided to contract thermal stresses in transverse direction, and made of dowel bar are made of mild steel round bar in short length. Of course, the length of the dowel bars has been designed. Half length of the bar is bonded in one cement concrete slab and remaining portion is embedded adjacent to the slab, but kept free for the movement during the expansion and contraction of the slab. So, there are two functions of the dowel bars. One is to take care of expansion due to temperature, expansion and contraction of the slab, because one end is fixed, it is embedded in one slab, and in adjacent slab the dowel bar is free to move inside. So, it is kept in a something hard cylindrical shape materials. At the end a cotton are placed. So, when there is a expansion, when temperature is rises, then there will be expansion. So, the dowel bar will move inside and adjust the length of the slab, increment or decrement. This is the one thing. Second thing is very important, that is a uniform transfer of stresses. As the vehicle is moving on the slab, and when second slab will come, the stresses will go on increasing as it reaches to the edge of the first slab. So, here the stress will be infinite in first slab. As the stress will infinite, then the sum part of the. So, here when a stress become infinite, then the sum part of this portion will break, and as is transfer the load from this slab to this slab, the action of second slab will be same as the first slab. But if you are providing here a dowel bar, then the stress will be like this way, and because apart from the joint, the stress will be counterbalanced by the dowel bars in the second slab also. So, in this way the load or stress transfer from one slab to another slab by uniform method, if you are providing the dowel bar. So, in this way the dowel bar is one of the most important factors that have been provided in the rigid pavement to just transfer the stresses from one slab to another by uniform manner. Otherwise, there will be huge cracks in these areas. Huge crack in this area, and this is the major defect of the rigid pavements. So, it is very necessary to design the dowel bar and properly placed inside the slab. So, in this way we have covered the entire things or parameters that are used in the rigid pavement, and we will discuss the design part in the next class. Thank you very much.